Here we have Electrostatics Field and Potential FRQ Practice from the Physics Honors Unit 6 curriculum, and this is a continued video from one I made earlier in this unit with more material to study. Here are some important formulas. Electric force, we've already been working with this one. Electric field on a point, electric potential on a point, and work. Over here, this will help us figure out the electric field at the origin due to a charge. Same idea here. It will help us find the electric potential on the origin due to a charge. And the work formula over here will allow us to determine how much work is needed to move a newly introduced charge to the origin from infinity. I will talk about that more when we get to it. Here's a scenario. A negative charge, Q1, negative 10 microcoulombs, is located at point X1, negative 3 meters. And a positive charge, Q2, 6 microcoulombs, is located at a point X2, which is 9 meters. So first, we want to annotate the diagram, figure out where everything is located, identify the origin, and basically gather up all the important information and condense it to one area where we can work off of, which is this diagram. So the first question, we wanted to figure out the direction and magnitude between the two charges. Right here, we just need to use the electric force formula, plug in and solve. This should be straightforward. We've already been working with this formula quite a bunch. The units is newtons, and you should get 3.75 times 10 to the negative third. Remember that the radius is the distance between the two charges on the number line, and since we are taking the absolute value of the charges, we can ignore the signs, positive or negative. Part B, find the magnitude and direction of the electric field at the origin due to Q1. You can pause the video, do this before I move on to the explanation for both charges. I will not be explaining how to do it for both charges to avoid redundancy in this review. So figure out both electric fields due to the origin based off of these two charges. I will only explain how to do one of them. So to complete the step, we must use the electric field due to a point formula, since we are trying to find the electric field at the origin. So we plug in our numbers, take the charge and the radius, and remember that we are also taking the absolute value, so we can ignore the positive and negative charge. This should have been negative, but again, we're taking the absolute value, so we can ignore that. Notice that the radius is also squared in the denominator, and you should get 1,000 newtons per coulomb. That is the unit, and the direction is attractive because the charge is negative. Part C, find the electric potential at the origin due to Q1. Again, pause the video, figure it out yourself. I will not be doing it for Q2 to avoid redundancy once again, and I will move on to the explanation now. So this time we are finding the electric potential, not the electric field on the origin, therefore we use a different formula. So use V equals KQ over R, plug in the numbers once again. We are not taking the absolute value, so this time we do plug in the negative 10 for Q1. And also notice that the radius is not squared in the denominator, so we are not squaring number 3. You should have gotten negative 30,000, negative 30,000 volts. That is the unit for this portion of the FRQ. So find the net electric potential at the origin, assuming that the electric potential at the origin for Q2 is 10,000 volts. So again, I did not explain how to do the electric potential at the origin due to Q2. You might have gotten a different number. I just said it was this number for easy computations in the explanation. So you might get a different value for the net electric potential because you might have calculated this one to be exact, but I just plugged in 10,000 volts. So we just need to use the total V formula, where we simply add the two V values we obtained previously in the FRQ. So it's just V1 plus V2. Remember, we are preserving our positive and negative signs in this computation. So we should get negative 20,000 volts. And part E, this is where we introduce the work formula. So how much work must be done to bring a 2.5 microcoulomb test charge from infinity to the origin? This is what I was talking about in the beginning of the video. We need to use the work formula. Work equals Q delta V. We already found delta V 2 slides ago, right here, negative 20 volts. So we just plug that in. And for Q, this is just the value of the charge we're trying to move, which is 2.5 microcoulombs, or 2.5 times 10 to the negative 6. We just plug in our numbers and we get negative 0.05 joules. Remember, we do include our positive and negative signs in this computation as well, and the unit for work is always joules. So in conclusion, I hope you learned something today that you can use on the exam. You learned how to show your work on each part of the Unit 6 Electrostatics Field and Potential FRQ. Make sure you understand how to use all of the formulas effectively and remember the units for each of the values computed. Additionally, computational errors are common if not inputted into the calculator correctly. Make sure you know how to use the calculator, parentheses, and all of that stuff. And use this information to completely and correctly complete the FRQ on the upcoming exam. If you have any other questions, reach out to your teacher, and that should be it. Thank you.